Hi everyone, we continue exploring our database tool. In the previous episode, we looked at the SQL command that we use to query the database and the programmed functions. In order to use these functions, we need some logic, and today we will stop on this in more detail. Also, in the comments, there were questions about what all of this is needed for at all, how this can be applied in real life. In other words, how you can make money with this knowledge. Today we will look at specific examples where our knowledge can be in demand. In the background, you now see one of the programs that works at one of the high-tech manufacturing facilities located in Silicon Valley. We will look also at some other programs, but everywhere you will see these two letters DB. And this means that if you have the knowledge that we are getting here, you can easily find a suitable job opening at any of these companies. Well, let's, for example, look at the job postings that are available where I live. Where you live, you surely have some kind of your own job service in your region. Let's see what vacancies are available in my region within a 25-mile radius. I go to the Indeed website and I will use the keyword LabVIEW database. As we can see, within a 25-mile radius, we have more than 500 job openings. Now we will not look at job responsibilities or positions, we just established that specialists are needed indeed. And now let's see how our knowledge can be integrated into practically any application. As we can assume, in every production line or service chain, there is a source of data that must somehow be collected and stored somewhere. We looked at the example of test stations in previous episodes. The data or data streams can, of course, be completely different, but the principle is always the same. We need to write this data into some tables and then have the ability to manage this data, to retrieve this data from these tables. Now we will look at some examples of completely real tools that are located at some stage of the production process. And then we will analyze where our area of knowledge is applied there and make sure that it is impossible to do without it. The first video that we will watch will be a station where the spectral characteristics of objects are studied. In the second video, we will look at a quality control process for microchips, and we will also find an application for our knowledge there, those cherished two letters DB. This is the first video where we see some process and we pay attention to the user's interface. I'll play it again. On the bottom bar here, we see the DB button. A little later, I will open the source code of this program, and we will see functions that we are already familiar with. Now let's look at the second video. Here we see an instrument that performs scanning of microchips. Now let's look at it on the software level and recognize the functions that we discussed in previous episodes. So, in the upper part of the screen, you see our database tool program, and in the lower part of the screen, you see the source code of the program from the first video. On the DB tab of the program from the first video, we see the same functions as in our database tool. Now let's look at these buttons on the block diagram. Let's find the terminals of the buttons DB refresh list, refresh table, auto size table, and DB search table. Here we see sub-VIs, sub-programs that use the database connectivity toolkit that we are already familiar with. Let's open the sub-VI. Here, of course, the logic is a little different. The logic in each case is unique. It is impossible to make universal logic because all processes are different. That is why in the future we will pay special attention especially to logic. Now let's look at another program. So this program is from the second video. I will open the tabs here so that we can see everything in this program. And here we'll also see our precious two letters DB. This will be here on page 10. This is our functional block where we effectively apply our knowledge. On the left side of the tab control, you see a programmed SQL function. This is quite a large SQL code that collects data from different databases from different tables. This SQL code is executed when we press the button Send Query. What changes here? In the program, the values change automatically. We do not enter them. They are loaded automatically. In this window, we see only the send command. We do not compose it ourselves. This is exactly the beauty of a programmed function. This is also the difference, for example, from PostgreSQL, or rather from the way of programming in PostgreSQL. And in this case, it doesn't matter in which language the program is written. In this case, it is completely written in the LabVIEW environment in the G programming language. We can always create a DLL file, short for Dynamic Link Library. This is a file that can be efficiently used in any text code and as an include application. We will talk in detail about creating a DLL later. For now, our task is to identify the application of our knowledge. We see that in every production or service cycle, our knowledge is in demand. At this point, I will finish the overview of the market and the possibilities of applying our knowledge, but we will be returning to this again in upcoming episodes. Let me digress for a moment here. Of course, in order to create multifunctional programs on our own, we still have a lot to learn. For now, we are looking at a very narrow area of programming in the field of database applications. Of course, if we want to create something more complex, for example, a robot like this or a robot dog like this, then we will need much more knowledge and effort. For example, to create the instrument that we just looked at for scanning microchips. If we want to build it from scratch, based on a technical specification, we will need not only knowledge of database programming, but also knowledge of programming in the field of actuators, that is, moving elements. Yes, and I will also open the tabs where I have the clock, so that you can see everything that the operator sees during the work process. So this is everything related to actuators. This is everything related to motion. We see it here. So this also relates to actuators. Here we see mathematical functions. We can assume that this is interpolation of positioning. Here we see geometric orientation. So, of course, knowledge of mathematics and geometry will be needed. Here we have ROI, region of interest, for video processing. Here we see many processes that are required to perform the given task. Therefore, we have to say that just knowledge of programming alone will not make it possible to create such a program that serves such a process. You have to know the process itself. If you give a regular person the best brushes and paints, he is unlikely to paint some kind of masterpiece. By analogy, if we have the best programming language, this doesn't mean that we can write something in it that is worthy of attention. Just knowing the syntax and the functionality of a program by itself does not mean that this is enough. For example, to create some instrument from scratch, just knowledge of programming may not be enough. You may need to create a CAD model. You may need to manufacture custom parts. You may need knowledge in the field of optics. Here we see 3 cameras on each microscope, so knowledge of video processing will be needed. LabVIEW has excellent tools for this, video acquisition software, and if we want full automation capabilities, then VDM, Video Development Module. Well, since we already touched on this topic, I will show you how video processing works using our IDE. But to finish with this picture, This is a CAD file made in SolidWorks. In the future, we will look at the capabilities of SolidWorks and how it interacts with LabVIEW. So in this picture made in SolidWorks, we see the functionality that we need to describe in our program. That is, we see that each microscope is located on its own actuator to provide focus, and there are also 5-6 more actuators that perform motion for full automation of the scanning process. So we can imagine that this is a robot by functionality. And it is no worse than the robot that I petted at the Museum of the Future in Dubai. Only that dog is not very useful, while this instrument does very important work. Well, since we already touched on video processing, let's spend just 1 minute looking at how defect detection on microchips looks in real time. Here we see the work of VDM. We will definitely look at this in future episodes. But here again, I would like to draw your attention to the database button. We see our familiar buttons, and here's the database. We see that everywhere our knowledge will be applied. Here we see that in real time a data stream is being written into the database, fetch, and I know a little about the algorithm of this program, and I know that there is a machine learning algorithm here. What does it mean in this case? This is when the recorded data, the result, that is, the score in this case, is compared by different parameters with already accumulated data. According to some principles, the maximum score is selected, and this is written for further comparison. In this way, we constantly improve our test. That is, we teach the machine, the computer, to make more correct decisions based on its own errors. So, we got a little distracted from our DB2 program, but I think this was an important digression. It gives an understanding of how much our knowledge will be needed and applicable. If our portfolio includes the database tool, the program that we are exploring in this series, then we will always find a suitable job opening, an application of our knowledge, and we will always be in demand. Let's return to our program and repeat where we stopped. Last time we stopped at the replace cell function. Let's once again repeat what we did last time, where we stopped, and look at the logic. So, here in this cell, we will replace the number 888 with 999, for example. I press the replace cell button, replacing one cell, and we see that the value has changed. Next, I open SQL query, and now we will send a command directly with SQL code. Let's set current 888, where current in milliamps 999. Everything is correct here, and I'm sending it, and we see that the value has changed. And yes, I included error handling in the programming here, in case there is an error. I'm going to deliberately make this error in the table name right now. Where a test station is, I will change the name of it. I wrote a non-existing table and table that we do not have. I send the query and I get an error. Now, let's understand at the programming level how all this process works. If I press power off and then start looking for the terminal, I will immediately get to the block diagram in the case that we need. As usual, here the command in our program is executed from left to right. And the first sub-VI that is executed is db SQL query. Here we see that windows and buttons have appeared that we do not see during regular program operation. This is the programmed size of our user interface for this subprogram. Let me remind you how we programmed it. File, VI properties, category window appearance, custom, customize, And here we see two checkboxes: show front panel when called and close afterwards if originally closed. That is, this giving us the ability to have a pop-up window when this sub-VI is called. And we define the size right here, window size. So, how does this sub-VI work? I should mention that here we have a while loop that runs continuously, and we can stop it in two ways, either by pressing the Send Query button or by pressing the Cancel button. After this program stops, we specified in our properties that the sub-VI, the pop-up window, is closed. In order to pass our commands from our subprogram, we use indicators. They are not needed for the operator, so we hide them. They are outside the visible boundaries of our sub-VI. Yes, this is how we hide them. So, we have a window called Send Query. In it, we write our SQL command that will access the database and execute what we requested. We also have another small window called for GUI table name. Since in this case the SQL command is executed independently, we need to specify in our program in which table the changes occurred, so that we can see them. So we created the command, specified which table it will be in, and pressed the Send Query button. What happens next? I return this sub-VI to its initial state, save it, and close it. We no longer need it. Now I open Context Help, and when I move the cursor over our sub-VI, we see that three terminals come out of our sub-VI: the SQL command, our Boolean Send Query or Cancel, and the name of the table in which we are working. If we click Cancel, we go to the false case, and in the false case, nothing happens, and we exit to timeout and wait for the next command. Let me remind you that here we have a state machine structure. This structure assumes that we are constantly in the event case timeout. We set the speed of our program to 100 milliseconds. This means that we check the measurement values of our controls 10 times per second. If we press the Send Query button, we go to the true case. Here the following logic is executed. We write our SQL command for execution into the sub-VI db send query executable, and we pass to the same sub-VI the value, the name of the table we are working with. We also write the state of db tables, and when our sub-VI is executed, we write the column names into our db table on the user interface, and we also duplicate our table so that it shows us the correct table name in the db table window. We also display the updated state of the db table and the number of rows and columns accordingly. Well, I kind of described to you how everything should work, and now let's see in the sub-VI how this actually works and why. What do we see here? Here everything is executed from left to right, yes, as always. We open our database, this command, this function, this mechanism we have already looked at many times. The next step is that we execute the SQL command using the function dbTools execute query. It executes an SQL query and returns a record set reference that you must eventually free with the dbTools free object VI. Wire data to the reference input to determine the polymorphic instance to use or manually select the instance. The next step is that we check whether there is an error on the error wire or not. If there is an error, we execute the dbTools free object function and close the database. dbTools free object frees an object by destroying its associated reference and returns a different reference object. Wire data to the reference input to determine the polymorphic instance to use or manually select the instance. That is, before we execute dbTools free object, we clear the error on the error wire using the mgi clear error function. Otherwise, this function will not execute. And before that, we write what error we had into the pop-up window, MGI error message. Where we get the MGI functions from, we discussed in previous episodes. Here we can also clean up the information that we consider unnecessary. And here, as an example, I remove the .vi extension from the error text and replace it with an empty space. Thus, if an error occurs, we get a one-button dialog that shows a pre-formatted error that is passed to us from the OLEDB error library. We also write 0 values into our row and column indicators and clear the table indicator and the column names, but at the same time we leave unchanged the name of our input table that we are working with. If there is no error in our SQL code and the command is executed successfully, then we go to the no error case and again do free object. That is, we prepare our database for the next operation and we send a very short SQL command. Select top 1000 all from the table name, which performs the following task. Select the top 1000 values. Why do we make such a limitation instead of displaying the entire table? Because to display 1000 rows, this will happen in real time quickly and we will not even notice how it happens. But if we, for example, put 1 million instead of 1000, this can already take from 1 minute to some significant amount of time, depending on where the database is located. If the database is located on a local network, it will naturally be faster, and if it is in the cloud, it will be much slower. Everything again is determined by the communication speed, so it is up to you what value to set here. I set 1000. Thus, we gave the command to display 1000 rows for us. The next function is dbTools fetch record set data. Retrieves the data in the record set identified by the record set reference input. You can convert each element in the array to its native LabVIEW data type using the database variant to data function. Wire data to the reference input to determine the polymorphic instance to use or manually select the instance. In simple words, it gives us unordered data for our query. Here, this is called variant data, which we then organize, knowing the cell types. In our case, this is string, and we output the ready data into our table indicator, and in parallel we count rows and columns. After executing database variant to data, we again do free object. That is, we free our database for the next action. Then, using the dbTools list column function, we request the column names and also output these values to the terminal. Yes, we output all the values to the terminals. Here they all are. So we can see all the terminals through context help. And when I close the sub-VI, we can also see them from our main block diagram, the same distribution of terminals. All that remains for me is to connect my indicators and property nodes, and my logic in this case is finished. We go to the timeout case and wait for the next command. Here I wanted to finish, but then I thought that since I have a program open that has a clock, I will take this clock and add it to my dbTool. So, maybe we place it here on the logo. No, not very good here. Yes, it looks better here. And for the clock to work, we will connect it in the next episode. In the next episode, we will continue exploring our database tool. We will stop in more detail on the logic. It's never enough time for the logic, huh? We will also talk about why all of this is needed for those who do not believe that this is useful and necessary. And this is very useful and necessary because if you have the skills and knowledge, completely different horizons open, and there is no limit for what you can achieve in life. Next time I will tell you about Elon Musk, and specifically about how, with the help of our program, he became a multi-billionaire. How, you will ask? Very simple. Elon Musk made his SpaceX developers work in LabVIEW. But more about this next time. That's all I've got for today. Thank you for joining Laplanda Tech. If you have any questions, please leave them in the comments. If you learned something new today, give this video a like and subscribe to learn more from upcoming episodes.